Hello everyone, my name is Tyler Kui. I'm PhD student in Leibniz University, Hanover. Today I would like to present my paper, Fair-capacitated clustering. My presentation includes the motivation, problem definitions with proposed method, evaluation and conclusion and outlook. As you know, that group assignment and student team achievement division are important in teaching and learning tasks to help students working together. And clustering algorithms are effective solutions for partitioning students into groups of similar ones. However, the traditional clustering algorithm focus only on the similarity objective and do not consider the fairness of the resulting cluster with respect to the two protected attributes like race or gender. For example, here we have a set of students, and if we do the traditional clustering, we may get the result like this. And if we see the number of male or female in each group are different, so the clustering algorithm needs to consider the fairness with respect to protected attribute. That's the fair clustering. If we see that the number of male or female in each group are equal. In addition, the algorithm needs to consider the size cluster. That is capacitated clustering problem, and we get the result like this with a number of instances for each cluster are equal. So we define a new problem by merging two problems that we call fair capacitated clustering, ensure the fairness and balance capacity of the resulting cluster, and we can get the result like this with number of male or female in each group are equal and the number of instances in each group are equal to. So this is the problem definition we call TKQ fair-capacitated clustering, with K is number of cluster, Q is the maximum cluster capacity, and T is the minimum balance threshold. Thus we try to partition the data X into a cluster C with K cluster. For each cluster Ci, the capacity of Ci lesser than or equal to the capacity constraints, and the fairness constraint is balance of clustering CE greater than or equal to the minimum balance threshold, and we minimize the objective functions. That's the sum of distance from any point to its center. In which the balance of one cluster Ci is the minimum of ratio in between male or female, for example. We propose methods based on the fairness. That is the minimum sets that satisfy the balance requirement. A fairness decomposition is clustering F into L small cluster. If X point in dataset X belongs to exactly one cluster Fj, and the number of instances in Fj is lesser than or equal to F plus M, and the balance of clustering F is balance of dataset X for Fj is a fairness, and here example for the fairness X small group is a fairness that satisfy the balance requirement. And we have two-phase algorithm. That's phase one, we compute the fairness decompositions, and phase two compute the cluster based on the fairness into K group, and the output is the clustering F is the fairness decompositions as the input of the phase 2. In the phase 2 we had two methods, hierarchical based approach and partitioning based approach, which hierarchical based approach we consider the capacity of final cluster in the merging step, and for the partitioning based approach we reformulate the assignment step of K-middle algorithm as a snapshot problem. Here snapshot problem is one optimization problem. For example, we are given a set of items, and each item has weight and values, and we need to select the set of items that total weight is less than or equal to a given limit, and the total values is maximized. The fair-capacitated hierarchical clustering. The first step we exploit we consider as a fairness, and given the number of cluster K, the maximum capacity, we will do the hierarchical clustering. In hierarchical clustering, we try to merge two small cluster into bigger cluster beyond the distance. And we can consider the capacity of the final cluster in merging step very easily, because we will know how many instances in the final cluster if we try to merge. For example, if we try to merge two big cluster into bigger cluster, we have the number of instances 8, but if the number capacity is 7, so it's violate, so we don't merge and we merge to other group. So if we continue into the end, we have one cluster. However, we given the number of cluster k, so we stop in one step. For example, if we stop here, we have 4 cluster. If we stop here, we have 3 cluster. So this is second method. That is the k-meter fair-capacitated algorithm. In this step, we need to formulate the cluster assignment step at a 0 collapse problem. So we need to define values and weight. So first one, for the weight, we define weight of each fillet is the number of instances for each fillet, and we define a values of a fillet is based on the diff functions based on the distance from the fj to si for each si is a cluster center. And we formulate the cluster assignment step as a 101 knapsack problem that we try to maximize the total values, and we control the weight, the total weight not greater than the given number q, in which yj is the plug variable, in which yj is 1 if fj is assigned to cluster and 0 if fj is not assigned to any cluster. So in general, we assign the most suitable fillet to each middle at I by the solution of 0-1 knapsack problem. Here is one example for the fair-capacitated clustering. This is method for k-meter fair-capacity algorithm. We select k-meter randomly, and then we use the solution from knapsack problem by the, to assign the fillet into the center. And then to optimize the clustering code, we try to swap non-Madoid with Madoid, and we see if the clustering code is reduced. We try to we will switch non-Madoid and Madoid. For example, we switch to other Madoids, and we reassign the cluster. We evaluate our method with 3 different datasets: UCI student performance, OLAP, and MOF dataset. When we experiment we compare our method with baseline k-meter vanilla fillets and MCF fillets, when we measure the clustering cost, balance score, and capacity with the formula on screen. This is a result from different methods on UCI student performance dataset. In terms of clustering cost, fairness, and capacity, with clustering quality lower better, clustering fairness higher is better, and capacity. So in general, our method outperforms the competitor in terms of clustering quality, because our method here and the competitor with higher clustering cost. With the fairness measure, our method can maintain the fairness above the minimum threshold. And for the capacity, we have here the maximum capacity with the dash line and dot line, blue and red line here. We see that our method can control very well the capacity, but because the variance in terms of capacity in each cluster is very small. For other methods, bulk loss very high. So we found that k-meter based approach is better than hierarchical based approach. It's similar on other dataset, OLAP and dataset, and the MOF dataset. So in this presentation, we propose fair-capacity clustering problem that's focused on the size and fairness of cluster, and our method are effective in terms of fairness and capacity while maintaining clustering quality. In the future, we will improve the clustering quality by optimizing cluster assignment phase and extend our work to multiple protected attributes. Thank you for your attention.